This program will provide participants with an introduction to the components of an injection mold and an explanation of some mold building procedures. At the end of this program, viewers will be able to identify various components of the mold and their functions, describe different cooling systems used in injection molds, identify different gate configurations and explain some of the reasons they are used, and explain some basic machining operations used in mold construction. Injection molds are usually made of two halves, which are held together or apart by the injection molding machine. Depending on the size of the part and the size of the molding machine available, molds are made with single or multiple cavities. The mold is generally made of tool steel and contains channels for heating, venting, and cooling. A mold includes a mechanism for ejecting a part once it has been made. A variety of ejector systems are used to eject the part from the mold. Injection molds are subjected to extremely high injection pressures, from 5,000 to 45,000 pounds per square inch. Today, companies are demanding tighter part tolerances which require more precise injection mold construction. In addition, most plastics will flash if a gap of 1/1000th of an inch exists between the steel. For these reasons, injection molds must be made of solid construction with an extreme precision. As you will see, injection molds are extremely costly due to the amount of time required for their construction. The simplest and most common type of injection mold is the two-plate mold. In this section, we will discuss the components of a conventional two-plate mold and see how they fit together. We will begin with the movable side, or the B side of the mold. Clamp slots are used to clamp the bottom clamp plate to the movable platen of the injection molding machine. The rails are mounted on the bottom clamping plate and the support plate to form a space for the ejection mechanism. Buttons are pressed into the bottom clamping plate to serve as a landing for the ejector plates. Pillars are used as additional support for the core retainer plate. The pillars keep the plate from deflecting during injection and packing. Bolted to the clamping plate, they are the same height as the rails. The ejector housing box contains the ejector assembly. In our example, we will use ejector pins to eject the part from the cores. The ejector plate consists of a pin plate and a retainer plate, which are bolted together to form a unit. Return pins are located in the ejector retainer plate and are used to ensure that the ejector plate and ejector pins return to the bottom position as the mold closes. The sprue puller pin is located directly under the opening of the sprue. It has an undercut and is used to pull the molded sprue out of the bushing after each shot. The support plate is used to keep the core retainer plate from deflecting during injection. The core retainer plate holds the leader pin bushings as well as the core blocks. In smaller molds, the cores are usually made of hardened steel, while the mold base is a much softer steel. This is the stationary side, or the A side, of the mold. The cavity retainer plate holds the cavity blocks as well as the leader pins. The 4 leader pins are used to ensure proper alignment of the mold halves. One leader pin is purposely offset to ensure proper assembly after mold maintenance. The top clamp plate holds the stationary side of the mold to the stationary platen of the molding machine. A locating ring fits into the top clamp plate and is used to ensure that the nozzle and sprue bushing align. The sprue bushing connects the nozzle of the machine to the mold. The sprue bushing is usually radiused so that it seals up against the nozzle. This allows the molten plastic to flow from the machine nozzle to the sprue bushing without leaking. Injection molds are cooled by water lines, which have been strategically placed throughout the mold. For efficiency reasons, the water lines are located at uniform distances from the cavities and cores. Mold temperatures must be carefully controlled to produce dimensionally consistent parts with a minimum amount of stress. Be sure that the supplied water is cooling the actual cavity and core, not just the mold plates. There are three methods used to cool mold cores. The first method is a bubbler type system, in which water flows through a brass or aluminum tube located in the center of the core. As shown, the water circulates along the length of the core. This is not the most effective cooling method because of the difference in surface area between the inside of the tube and the inside of the core. The second and most common method is to install a flat brass baffle. The advantage of this method is that there is a greater volume of water to cool the inside surface of the core. The third and most effective way is to insert a spiral tube through the center of the core. As shown, a large volume of water flows through the tube at a very fast rate. Effective cooling of mold cavities is accomplished by locating water lines at even distances within a cavity block. Runners are channels which connect the sprue bushing to the mold cavities. Runners should be as short as possible to reduce cooling time and the amount of scrap. They should also be the same length. For multi-cavity molds, it is important to use a mechanically balanced runner system so that all the cavities fill at the same time. When the cavity layout or the shape of the part makes it impossible to provide the ideal runner system, a branched runner system may be used. The gate is the narrow, shallow portion of the runner as it enters the cavity. Gates are located on an area of the part surface where they cannot easily be seen and can readily be trimmed on the finished part. They should be located so that the flowing material hits an opposing wall as soon as possible after entry into the cavity. If material enters a thick section or rib area, sink marks may appear on the part. The type of gate used depends on the part design and the characteristics of the material. The direct sprue gate allows the material to flow directly into the cavity. A disadvantage of this type of gate is the large amount of material at the intersection of the sprue and the part that must be cooled, leading to a longer cycle time. Another disadvantage is that the sprue needs to be machined off of every part. The edge gate is the simplest design used on injection molds. Once the part is molded, it simply breaks from the runner. A tab gate is used to obtain a better flow pattern by absorbing any strains and imperfections in the material. When running clear materials, the tab picks up the haze, allowing the part to be completely clear. In general, an extra operation is required to remove the tab. A fan gate is used to improve flow by dispersing the material into thin parts in a wide pattern. They are generally used for flat designs where warpage needs to be minimized. The submarine or tunnel gate allows the part to be degated as it is ejected from the mold. The gate goes below the mold parting line so that the mold can mechanically degate the part from the runner. A pinpoint gate is used on 3-plate molds. This gate is also mechanically degated from the part as the mold opens. Now that we have discussed some basic mold components, let's look at some of the machining practices for building molds. Milling provides a way to remove large amounts of steel very rapidly. On small parts, milling brings a part to roughly the right dimensions, but another more precise machine operation is needed to bring the steel to its final dimensions. For this reason, milling on small parts is referred to as a roughing operation. However, large plastic parts generally have wider tolerances, which are met acceptably by the milling process. Milling is done prior to heat treating because it is difficult to machine the steel in its hardened form. This is why it is beneficial to remove as much steel as possible prior to heat treating. Typical operations prior to heat treating include drilling water lines, ejection pinholes, and machining pockets for inserts. The part to be milled is mounted on a milling table, which moves left to right and up and down. Turning the steel in a lathe is also considered a roughing operation. This process also leaves a swirl pattern on the steel. However, it is a preferred method for rapidly removing large amounts of steel from cylindrical parts. Grinding is the most accurate method of machining steel. Steel is ground in the hardened state because the abrasive stone wheel works best on hardened steel. Grinding soft or unhardened steel tends to gum up the wheel, requiring the wheel to be redressed with diamond. Since diamond is harder than the abrasive stone grit, it is used to clean and shape the wheel. A radius dresser allows us to accurately machine a radius or form on a grinding wheel. Another accurate method of machining is called electrical discharge machining, or EDM. EDM allows us to machine difficult forms into any steel, whether soft or hardened. The first step is to machine a carbon electrode. Electrodes are easily machined and can be made quickly and accurately. Grinding is the method of choice for machining electrodes because of its precision and accuracy. The electrode is a mirror image of what is to be machined into the steel. The electrode represents what the actual part or detail would look like once molded. The EDM operation removes steel by passing a series of electrical discharges between the electrode and the steel at a controlled interval. Both the electrode and the steel are submerged in a dielectric fluid. Electrical discharge machining equipment is very expensive, and the process is extremely time-consuming. Once the steel has been machined, the surface finish of the steel must be reworked by hand to eliminate the grit-type finish. Final handwork is required after the cores and cavities have been machined. Since the molded part's finish is dependent on the surface finish of the mold, stoning of the cores and cavities is done using progressively finer stones to achieve a desired surface finish. Polishing stones are made of fine stone compressed into a stick form. A diamond paste can be used to work the steel to a flawless type mirror finish. Now that we have reviewed basic machining operations used in mold construction, we will explain some procedures for proper mold maintenance. Molds should be cleaned during production at least once per shift. The molten plastic produces a residue which builds up on the mold surface and needs to be removed. If it is not removed, it may build up to the point where it must be machined off, which can be very costly. When cleaning molds, be sure to use soft cotton swabs so that you do not scratch the mold surface. In addition to the cores and cavities, be sure to thoroughly clean the vent areas. If parts begin sticking to the mold during operation, try to remove them by hand. If this is not possible, use a soft metal object, such as copper, brass, or aluminum, to pry the part out of the mold. Sometimes a polyethylene or wooden rod can be used to work out a stuck part. Never use screwdrivers or pliers to remove the part, as this may damage the mold surface. If the mold needs to be stored after a production run, it must be thoroughly cleaned and greased. Spray the inside and outside of the mold with a mold saver or rust preventative. Check the water lines to be sure they are functioning properly. Mold should always be stored in a clean, dry area. Proper care and maintenance will extend the life of any mold. In this program, we have seen the components of an injection mold and their functions. Different cooling systems used in injection molds. Examples of different gating configurations. Some machining operations used in mold construction.